Hey everyone, let's begin with the first module of Engineering Mathematics Semester 3. The first module is actually the continuation of the chapter Matrices and Determinants, which we studied in our plus 2 classes. Here in this module, we'll be focusing on square matrices. Today, in this video, we'll be discussing the topics Eigenvalues and Eigenvectors. To begin with, let's start with the concept of characteristic equation. For that, first we consider a square matrix A of order n and an identity matrix I, also a scalar quantity lambda. This is the nth order square matrix and the scalar quantity lambda, which will be unknown to us in the questions we practice, which is multiplied to the nth order identity matrix, and the determinant of this particular matrix is evaluated. If we equate the determinant of this matrix to 0, we get an equation which is known as the characteristic equation of the nth order square matrix A. Certainly, this characteristic equation will have roots, and those roots are known by the name characteristic roots or eigenvalues or latent roots. So in simple terms, what is characteristic equation? For a square matrix A, the equation obtained by evaluating A minus lambda I equal to 0 with lambda as the only unknown value. After evaluating the determinant, we get an equation in terms of lambda, and this equation when equated to 0 will give us roots, and these roots are known as the eigenvalues. Here in this question, we considered a 2 by 2 square matrix, so the identity matrix I will also be a identity matrix of order 2. After evaluating the determinant, we get the equation whose roots give us the eigenvalues of the corresponding 2 by 2 matrix. Let's pass on to the next concept, which is eigenvectors. If you consider the matrix multiplication A minus lambda I into x equal to 0, where x is a column matrix, x1, x2, etc., xn. When you consider this equation, it has a 0 solution when all the entries of x, x1, x2, etc., xn are equal to 0, which is also known as trivial solution or the 0 solution. We are interested in the non-zero solution of this particular equation. So the condition will be that this coefficient matrix will be a singular matrix, or this coefficient matrix will have a determinant which is equal to 0 to provide us the non-zero solution or the non-trivial solution. This multiplication will yield us a system of n linear homogeneous equations, and solution matrix x1, x2, etc., xn is known as the eigenvector. So in simple terms, what is eigenvector? It is the column matrix which is the solution matrix of the matrix multiplication A minus lambda I into x equal to 0. To understand the concept of eigenvector, let's take the same example. If A is the square matrix 5, 4, 1, 2, we already evaluated the eigenvalues using the characteristic equation A minus lambda I equal to 0, which provided us the roots lambda equal to 6 and 1, which are the eigenvalues. Since there are two eigenvalues, we will get two eigenvectors corresponding to lambda equal to 6 and lambda equal to 1. So let us denote x1 as the eigenvector for the eigenvalue lambda equal to 6. x1 is a column matrix x1, x2. A minus lambda I into x1 is evaluated. We replace the value of lambda by lambda equal to 6. After reduction, we get a matrix of this form. This matrix, when equated to 0, we get the values of x1 and x2. There is a shortcut method to find out the values of x1 and x2. To find out x1, just like we evaluated the determinant or the adjoint of a matrix, what we do is we hide the first row and the first column. The left out value minus 4 is written as the denominator of x1. To evaluate x2, we know that this position will have a negative sign multiplied. To find out the denominator of x2, what we do is we hide the second column and the first row. The left out value is 1, and this position involves a multiplication of negative sign which is multiplied and written here. So we get a ratio of this format. Minus 1 is the common factor. Taking out the common factor, we have x1 by 4 equal to x2 by 1. Looking at these ratios, we can write the eigenvector corresponding to lambda equal to 6, which is x1 is equal to 4, 1. So this is not only the unique answer for the eigenvector corresponding to lambda equal to 6, any non-zero scalar multiple of this particular eigenvector will also be a solution for this particular eigenvalue. To find out the eigenvector of eigenvalue lambda equal to 1, we follow the same steps. A minus lambda I into x2, where x1, x2 is the required solution matrix or the eigenvector. We substitute the value lambda equal to 1. So this is the resultant matrix. From this matrix we are going to find x1 and x2. x1 will have the denominator 1 and x2 will have the denominator with a minus sign multiplied by 1. So the values of x2 will be 1 and minus 1. So if you multiply this particular eigenvector by a scalar quantity 2, you get the answer 2 minus 2, which is also a right solution for the eigenvector of lambda equal to 1. Any non-zero multiple of x2 will also be the eigenvector of lambda equal to 1. Let's look at another example to understand the concept of eigenvectors. If you have a 3 by 3 matrix and you have to find the eigenvectors of the matrix, first we find out the characteristic equation, which is determinant of A minus lambda I equal to 0. We know that the matrix will look like this, with the diagonal entries having the lambda value subtracted from their original values, which when equated to 0, in this case we get a cubic equation. We check for values like lambda equal to 1, minus 1, 2, minus 2, etc. and we identify that lambda equal to minus 2 is the value which satisfies this cubic equation. So lambda plus 2 is the linear factor for this cubic equation. We divide this cubic equation by the linear factor lambda plus 2 to obtain a quadratic equation like this. We reduce this quadratic equation to linear factors and we obtain the 3 eigenvalues. So we will have 3 eigenvectors corresponding to each of these eigenvalues. For evaluating the eigenvector of lambda equal to minus 2, what we do is we first consider A minus lambda I into x equal to 0. What is x? X will be the eigenvector x1 with the column entry which is a column matrix with the entries x1, x2, x3. We replace the position of lambda by the value lambda equal to minus 2 and we get the matrix in this format. To find out x1, x2, x3, we follow the same process as we evaluate the adjoint of a matrix or determinant of a matrix. To find out x1, what is the process? We hide the first row and the first column. Then you take the determinant 7 into 3 minus 1 into 1. The value is written as the denominator of x1. In the position of x2, we know that always negative sign is associated. You hide second column and first row. Then you get the answer as 1 into 3 minus 1 into 3. Here it is a 0 value. To evaluate x3, you hide third column and first row and evaluate the determinant as 1 into 1 minus 7 into 3. You take out the common factor 20 and you get these values. So what will be the resultant eigenvector corresponding to lambda equal to minus 2? It will be 1, 0, minus 1, which can also be written in this format. This is not only the unique answer. If you multiply it by 2, you get 2, 0, minus 2, which is also an eigenvector for lambda equal to minus 2. If you multiply it by minus 1, you get minus 1, 0, 1, which is also another answer possible for the eigenvalue lambda equal to minus 2. In a similar way, we can find out eigenvectors for the eigenvalues lambda equal to 3 and the eigenvalue lambda equal to 6. So we get total 3 eigenvectors for 3 eigenvalues. Thank you for watching till the very end of this video. Have a nice day.